Hi, I'm Jonas. I'm here to talk about hybrid rocket engine injectors. I've written this report in association with Propulse NTNU, who are a recently started student organization who are building a hybrid rocket this year. An overarching objective with this report was to add to Propulse's relatively fresh knowledge base on rocket science. They've just started, so this document could be something that new members this year and in the future could read to quickly get into hybrid rockets and how injectors in particular work. Specifically, I've looked at how the mass flow rate behaves through the injector and how it can be controlled, as well as how the injector can be used to affect the performance of the rocket. So to begin, let's introduce the concept of a hybrid rocket. So for any combustion, you need an oxidizer and a fuel. And in a hybrid rocket, the oxidizer is stored as a liquid up here in the tank, while the solid fuel is stored in the combustion chamber in the form of a cylindrical fuel grain that's solid with a hollowed out circular portion running through it called the port. This here is a pressure fed system, which means it's not using pumps to drive the flow, but the pressure differential between the tank and the chamber. And so as you open the control valve, the flow goes through the injector and is then sprayed into the combustion chamber. So the injector breaks it up into tiny droplets. This is called atomization. And this helps the liquid oxidizer evaporate quickly so it can be used for combustion. Then the pressure and thermal energy builds in the combustion chamber as the combustion happens, and the flow is accelerated through the nozzle to very high velocities. And the thrusting force that propels the rocket forward is the product of the mass flow rate going out multiplied by that velocity. So there are many advantages and disadvantages to hybrid rockets. The most primary advantage is the inherent safety of a solid fuel grain that's completely inert. It's just essentially a piece of plastic or wax, so it can't just explode. The main disadvantage, however, is that they generally produce relatively low thrusts. The reason for that is that historically they have pretty low regression rates. The regression rate is how quickly the rate of change of that radius in the hollow section of the fuel grain. So essentially, it's an analogy to the fuel mass flow rate, how quickly it evaporates. And if the fuel mass flow rate is low, then the overall flow rate is low, and so the thrust will be as well. Now, the analysis of this is quite complicated. I won't go into it here, but essentially it turns out that the most important factor for that regression rate is the mass flow of oxidizer. So we would like to get an idea about how that works. So initially I thought to make a CFD approach, but I was quickly advised not to do that because of the incredibly fine meshes you would need in that atomization part. So instead, I've employed theoretical models on a simple orifice that you can see in the picture. So the parameters there are what's generally known, and you use that to calculate the mass flow rate. I won't go into the mathematics, but they're generally derived from continuity, energy, conservation of energy in different forms, and isentropic relations, in addition to other assumptions. So the first models that I looked at were single-phase models, single-phase incompressible liquid and the perfect gas model. We're not going to talk about them, though, because I don't have time, and because Propulse has chosen to use nitrous oxide as the oxidizer this year. The reason for this is that nitrous oxide has a very high vapor pressure, and this means that it can essentially self-pressurize the tank. You don't necessarily need an external pressurizing gas, but you can still use a pressure-fed system that doesn't require advanced turbopumps. The difficulty with nitrous oxide is that when it flows through the injector, it's exposed to the lower pressures in the combustion chamber, and so two-phase flow begins to develop through the orifice, so it's a lot more tricky to model. However, there are some models for two-phase flows. The first one being the homogeneous equilibrium model, which assumes thermal equilibrium as well as that two phases have the same velocity. And here are some calculations I've made for those. Now, an interesting point to note here is this dotted line. So that's what the model is actually predicting. But we know from experimental results that when the mass flow rate hits a maximum for gas and two-phase flows, you reach something called choked flow. So the mass flow rate does not change for further reductions in downstream pressures beyond the maximum. Now, this can be quite interesting because if we want to have a stable mass flow rate and we could operate in this regime here, pressure oscillations in the combustion chamber that tend to happen would not affect the mass flow rate. You just move back and forth here, potentially. So that can be used to control the mass flow rate. The final model here is the Dyer model. This one I just finished up with, and it's potentially one of the more accurate models. It doesn't assume thermal equilibrium or it's not homogeneous either. But it may be a case that for our case, it's not actually that applicable. I won't go into the details, but potentially it could be used. Yeah, so now let's look at some different injector designs. So far we've just looked at a simple shower head with straight injectors, but here we have an impinging design where the orifices are angled against each other so that streams collide onto each other and they break up more. So this aids the atomization process, which is good for the combustion. I won't talk too much more about that, but the next type are called swirl injectors. So here you use tangential inlets through here, and then the flow swirls through in this swirl chamber and is ejected in a hollow cone that is swirling. Now, swirling flow has been shown by hot fire experiments to significantly improve their regression rates, and often by like a factor of 2.7, I think is the number that keeps showing up, but it depends on the case. And this is because the centrifugal force of this swirling flow pushes the flame closer to the fuel surface, which increases the heat transfer. Additionally, there's something about the tangential velocity component increasing the effective oxidizer mass flux that governs the regression rate. The final type I want to show you are called vortex injectors. These also introduce a swirling flow, but they do so with inclined orifices in a certain pattern. And the advantage of this method would be that you can reap some of the benefits of swirling flow while it's seemingly far easier to manufacture. So this could be quite interesting for propulsive purposes. So to conclude, we've seen that the performance can be significantly affected by various injection schemes. We've seen that the mass flow rate can be held constant for a given upstream pressure. Now, in reality, the upstream pressure will probably not be constant, but this is something to keep in mind anyway. Our models can be used as an initial starting point for design to give you a ballpark estimate of what the mass flow rate will be, but they are not always that accurate. So in the future, we'd like to do experimental testing on cold flow as well as hot fire testing, and we can compare the different injection schemes to the models as well as against each other in terms of performance. And we could also do some further calculations with the upstream pressure as a variable, as well as more research into the characteristics of swirl and atomization especially. That's it.
Thank you.